So we're working through the wrestling exercises, and we'll start that up here in a second. I will say, so normally I do this on Tuesday and Saturdays from 10 to noon Central Time. I missed last week. I met last Saturday. The original reason I was going to miss last Saturday, I was going to be in Minneapolis at Mini Bar, a tech event. But in fact, last Thursday late, I dislocated my left kneecap, and I was driving to Minneapolis was totally not going to be an option. So all that got canceled, and I'm still dealing with the kneecap thing. And as a consequence, sitting here is not super comfortable. Like sitting, I tend to move a lot between sitting and standing. So we'll see how 2 hours of this goes. I think it'll be okay, but if at some point I'm just like, yeah, my knee hates me, it would be good time to either take a break, quit early, or just stand for a little while. We will deal with that as it comes up. Fingers crossed, nothing like that will happen though. Okay, can people hear me actually? I'm hoping that my audio is actually a happening thing. I guess I should ask that in the chat. Can people actually hear me? Yeah, cool. Thank you. Well, then let's go ahead and get started. We had left off. We've done about a little more than half of the wrestling exercises in the previous episodes, and we are now starting with generics, and we'll pick up there and see how much we can do in 2 hours. So this is generic types, so the ability to say, a vector of something, so you can specify a type like vector without tying it to a particular type for the contents, the things in the vector. But because of Rust's strong typing, we do need, the compiler needs to know at runtime what's actually in the vector for any particular vector. And in fact, in a way that's not unlike C++, the Rust compiler will actually generate different binary for each type of vector. So if we have a vector of strings and a vector of ints, well, let's say I32s and a vector of U64s, the compiler will generate different code for each of those kinds of vectors. And it can optimize that code according to the type, which is neat. I must say, when I first sort of learned that C++ was doing this, like back in the 90s, I found it weird. It seems odd to generate kind of the same code multiple times. But I mean, this is the compiler doing it, and so the duplication issues that we might have with human duplicate code don't necessarily apply. And the fact that it can do the optimization that it does is kind of nifty. So here we have a very simple problem. We create a shopping list, declare a shopping list that is a vector, and we call vec_new to create the initially empty vector, and then we push the string milk onto it. This doesn't, well, actually the stir slice milk onto it. This doesn't compile because question mark's not allowed here. You have to actually specify a type. You have to say what kind of thing shopping list is going to be. And since shopping list is going to be, since this is a stir slice, I think that we want, oops, this. And see if this works. Yay, it does. Now I have a feeling we could also put string here, and that it would do some kind of nifty coercion-y thing. Am I right about that? No, No, it actually has to be a stir slice. It will not construct a string out of a stir slice. I think, yeah, so constructing a string out of a stir slice would force it to allocate memory on the heap and copy the string data into that new capital S string object, because it wouldn't know for sure where that stir slice was or who controlled it. And it doesn't want to do that for you. It wants you to make the decision to do that copying. It will go the other way around. It can go from a capital S string to a stir slice, because all it needs for a stir slice is a pointer and a length, and it can get those out of a string. So, okay. So we do have to do that. It has to be a stir slice. Okay. Questions? And suggestions, comments, assistance, always welcome. There are often people here who know Rust way better than I do, and so certainly good ideas, helpful hints, greatly appreciated. Okay, so we move on to generics 2. This powerful wrapper provides the ability to store a positive integer value. Rewrite it using generics so it supports wrapping any type. So we have a struct wrapper, which holds a U32 value, and we have a constructor for that. And in our tests, we just create some wrappers, and the second set of tests fail because we provide a string to new, and new here wants a U32. So this test passes, but the second test fails. So we need to genericize wrapper, and so I think we just want to make that wrapper T and value of type T. So we're saying wrapper will be dependent on some type T, and value will then have that type, and then our impl is gonna take a T and return self. And I don't think this will work. I think we need to say something about T at the front of this. Yeah, so when we impl wrapper, we have to say this implementation is dependent on type T, and so this is kind of where we're declaring the type variable, which we then refer to here, and that's not enough either, because I think we need, does that go here? This is where I'm a little fuzzy on things. I know, yes, okay. So actually I find this syntax weird, and I'm not sure I feel super comfortable with it. The way I think I understand this is that we're saying we're going to implement something, and our implementation, whatever that implementation ends up being, depends on some type T, and we can declare one or more types here, 0 or more, because we can leave it out, and that's essentially declaring 0 types. But we can declare one or more types here, and then we can use that type elsewhere, and we have to use it here to say we're declaring value to be of type T, and I think we have to have this one. Let me make 100% sure. Yeah. So we're sort of declaring our type variable here, and then we're saying we're doing an implementation on wrapper of type T, and we need the T to sort of fill in this blank here, and then we can use the T in the body. And I find that double T here always looks a little weird to me. I can imagine it's a necessity, but it also seems odd that it can't do some simple inference to figure out what the dependencies are out here. Yeah, I don't know. I don't have wisdom on this, which makes me sad. That's a thing I guess I should try to understand better. Um, oh, what if T was a type? So you're suggesting what if we had an implementation for wrapper of a particular type? Ooh. Is that, let's see if I comment that out. Impl wrapper U32 pub fn new value U32 to self wrapper value. Does that compile? Yeah, that compiles. Oh, well done. I think that's the answer. That is very cool. Okay, so you could have specific implementations for particular types, and then I guess we could probably also then have both of these. No, it doesn't like that because these overlap. Yeah, so because it doesn't know whether to use this one or this one in the case that it's a U32, so I can't have both of them. But I bet there could be a circumstance where I could have a fixed set of types, or maybe I don't even want to, I only want to implement a particular function for certain types, and for other types I don't even want it to be allowed. Then this makes a lot of sense. Yeah, so that does, thank you. That is an excellent suggestion. So that we do need to say here that this is, whereas this is a impl for a particular type, here we're going to have an impl that depends on some generic type, and then we get to use that type in the appropriate places in the declaration of the struct and in the typing of value. Well done. I like that. Okay, so I'm going to get rid of this. That was a good suggestion. See, I'm learning stuff. That's nifty. So then generics 3. An imaginary magical school has a new report card generation system written in Rust. Good for them. Currently, the system only supports creating report cards where the student's grade is represented numerically between 1 point. I don't know if, no, that's not really a range, I don't think. That's just examples. However, the school also issues alphabetical grades A+ to F- and needs to be able to print both types of report cards. Make the necessary code changes in the struct report card and the impl block to support alphabetical report cards. Change the grade in the second test to A+ to show that your changes allow alphabetical grades. So let's actually find the second test. So I assume that's the first test, and then this is the second test. Okay, so this grade here is going to need to be an A+ instead of a 2.1. And they've got it probably as a number, so the thing will even compile. So, okay. So let's look at the struct. So presumably, since we're in the generics, we want to allow the grade to be any of several types, in this case either an F32 or a string. So we can say we're going to have T here, and grade is of type T. And then now that means we're going to have the impl T report card business like we saw before. And I think that the grade we're going to have to call something like toString because we no longer know what grade is, because it's, well, we know it's of type T, and we need it to be a printable object. So if we do that, what does that do for us here? Oh, no. Okay, so T does not necessarily implement display, and so we're going to have, so we can't call toString on just anything. So that would be a difference from, say, Java, where everything toStrings. In Rust, only things that implement the display trait can toString. So we're going to have to require that T implement the display trait. We need this to be that. Hey, so one of our tests passes and one of our tests fails. The second test fails because Gary Plotter, we're supposed to change the grade here so that Gary gets an A+ instead of a 2.1. So I think we can just say A+. And yay! So it, so we were made the report card generic over T. We had to do the whole impl business like we talked about on the previous one. But T couldn't be just any type. T had to implement the trait display. And we could also probably have done this with like debug, but display's nicer because it'll actually work in production code. And both the types that we were planning to use, a U32 and a string, implement display, so we're good. Oh, and apparently I can remove this and it will do the toString for me. It'll auto, look at that. Yes, very nice. That is nicer. Now, if I had not had the toString and I had left this out, it still would have said I needed, I need display. Yeah. Oh, and actually the help was even more useful because it explicitly said where to put it. Although I think, yeah, that's interesting. So I think that error message was better without the toString, strangely enough. Huh. Interesting. So it will format bang, will convert these things to strings as it can. And that requires, in this case, that T implement the display trait, and both U32 and string do that. And so we're in good shape. Cool. That is awesome. Excellent. Questions, comments? Boom. Then we're on to options. Close those guys. Close that up. Open up options. Okay. You can modify anything except this function's signature. So print number returns an option U16 and it unwraps that option and prints it. And the problem is we call print number with actual numbers, not options. And we need options for this to work. So we're going to need an option has either the sum or the none possibilities. None clearly is not the right thing here. So it's pretty obvious we need sum. We're going to need it here as well. So let's at least take care of those two things. Now, okay. So mute numbers is going to be an array of 5 option U16s. And we are going to iterate through 0 to 5. We're going to compute a number to add. And we're going to try to assign. So numbers is an array of options. So this needs to be a sum. I think that may, nope. It says to remove the mute, but I don't think that's going to be a good idea. I think that this is the actual problem. Because I think, well, I don't know, do we? Let's see what happens if I remove the mute. I think the mute has to come back, but I could be wrong. Well, let's actually solve this other problem, and then maybe the mute will return to us. Okay, so the problem here is that numbers has never. Oh yeah, so I bet we do need the mute, and we just need to assign numbers to something. So this declares numbers to have a particular type, but it doesn't give it a value, I think is the problem. And so we don't have a value for this array. So let us, let's see, arrays. Yeah, so here, for example, we're seeing that we've got a declaration. This gives it a type, but doesn't give it any values. We can initialize them all to have the same value here by specifying a value and how many we need. And so that seems like that might be a useful thing here. Equal 5. Now we would have an array of 5 zeros. And now it will compile. Whoa! Oh no, can't have a number there because this is an array of options. That was the whole point of the exercise. Hey, now the code compiles and we work. And obviously my choice of 0 here was entirely arbitrary. We could choose 17 and it'll still do stuff. Yeah. Because it never really does anything with the numbers array at the end. It just compiles it and does the work. And so this gives us an array of values, so numbers is meaningful. The mute is necessary. Let me confirm that. Yeah, the mute is necessary because we're going to assign something down here. And if we didn't have mute, that wouldn't happen. The iter as usize, presumably iter must be something else. I don't know what its type is. It's a thing in a range. And I suspect that that's related to the range type in some fashion. But it clearly isn't actually just a straight up int, but we can make it something by doing the as usize, and it will cast appropriately into that thing. So cool. Okie dokie. Now options 2. So we have an optional word. Word equals optional word. Oh, that's interesting. I don't know that I knew this syntax existed. So if we can treat an option kind of like an if statement. And so instead of saying if let some blah blah blah, we can just say optional word and assign it, and it will. Does that work? Maybe this doesn't work. Oh, it doesn't work. So yeah. So they say use an if let statement. Okay. I was like, really? Does this do a thing? Let some word. Undo. Okay. So this looks more plausible to me, and we'll maybe compile. Yeah, so that part compiles. So here we're saying if we can do this pattern match, so if optional word has the form some word, then we will do that pattern match, and the let allows us to assign, or in this case shadow. Oh no, actually we're creating new variables here. Assign a value to a new variable here. If this succeeds, then we will do this branch, and we will do it in a context, in a scope where this declaration and assignment has happened. So we can actually talk about word here and it'll work. Otherwise, we can do things, but we wouldn't have access to the contents of the sum because there weren't any. So this would happen if that option was a none. So this should work, and it should print the word as Rustlings. Mute optional integers vector. So we got a vector of option of I8s, and we're going to loop from 1 to 10. We're going to push some x on here. That's all very awesome. And then we're going to, so this doesn't work. So they suggest make this a while let statement. Remember that vecpop also adds another layer of option t. Oh, yeah, so pop on a vector returns an option of its own because it might fail. If the vector's empty, pop will return none because there's nothing to pop. And if the vector's non-empty, then you'll get a value wrapped in a sum. And since it's a vector of options, we'll have sum of a number when we get something. So a while let. So what we're going to do instead is we'll have while let some integer equals optional integers vec dot pop, and now I think that will continually pop, and as long as we match the sum case, the outer sum case, which also then will contain a sum integer because that's what we push on to the vector, then we'll print. When the vector becomes empty, we're going to get a none from this pop, and the while will fail and we will be done. So fingers crossed that will do the right thing. Whee! And we get the values in reverse order because the last thing we pushed on was 9, and so it'll be the first thing that we pop, and so we get 9 through 1. And just to amuse myself, I'm going to actually confirm that if let, that we get the because when I put the none here, optional word is a option type, but it doesn't know what that option type might contain. So we could, if we cared, if we really wanted to see this happen, I could do that. Yeah. And then we get the optional word doesn't contain anything. Okay. So that's interesting. If with the sum version, it can infer the parameterized type for option to be capital S string, but with the none, it doesn't have any way to infer that. And then there's a suggestion, try pushing a none on. Yeah, so if we pushed a none on to the vector, then that would fail this match and we would leave the while loop right away. So if we were to do optional integers vec.push none here, then we will print, oh, I lie. Oh, because it's at the bottom. We really want it to be, if I put it at the top, then now I think we'll print none of the values. So it doesn't fail, but it doesn't do what we expected because the top values in none, that doesn't match this pattern, and we don't do the while loop at all. We could presumably also handle some other cases here if we wanted to deal with that. But yeah, in this instance, and if we inserted a none somewhere in the middle, so if we were like, I don't know, if x equals 5, optional integers vec dot push none, now we'll get like half of the values and then we stop. So we get 9876, and the none went after the 5, so we popped the none between the 6 and the 5, and then it died. Loop ended, and our vec still has got stuff in it. So, yeah, cool. Awesome. And now I think we'll get everybody again. We put the world back the way it was. Yeah, it's a good suggestion. Thank you. Other stuff? Should we move on? Options 3. Boom, boom, boom. Okay, so we have struct point, then x and a y, I32. Y is an option point, has a value. So we're going to use match here. If match matches some p, then we'll print the coordinates. Otherwise, we'll say no match. And fix without deleting this line. So we can't refer to y here because the match took ownership. Point doesn't implement the copy trait, so we need to borrow in this pattern match. Now it says ref. Can I do just ampersand? No, doesn't like that. But it does like that. So ref p. I'm not sure I know. Rust ref. Ref annotates pattern bindings specifically to make them borrow rather than move. It does not affect whether a value is matched, only how it is matched. By default, match statements consume everything they can. Using the ref keyword, the value is only borrowed, not moved, making it available for use after the match statement. Oh, well, I didn't know that. Oh, and ampersand versus ref. Ampersand denotes that your pattern expects a reference to an object. So by putting an ampersand in, I was changing the type of the thing in some ways. And so ampersand is part of the pattern, whereas ref is not part of the pattern. It is merely an indication that we want to make sure that borrowing is done instead of consuming. Oh, okay. Well, I didn't know that, but I do now. And that was pretty straightforward. But now, trick is, am I going to remember that later? Too many things in my head. Okay, so now we are off to traits. Very exciting. Traits. Haven't done a lot with traits. So this will be useful. Your task is to implement the trait append bar for the type string. Let's see, there's ampersand does the contrary to what one would normally expect in pattern match. It actually eliminates an ampersand if it is a match. Yes, right. So it literally is pattern matching the ampersand. So if there's an ampersand in the pattern, there has to be a corresponding ampersand in the thing we're matching against, and those line up. And as you suggest, kind of like pew, take off together. So, yeah. And so that's why you need something like ref, because you want to be able to say borrow, and you can't use ampersand for that because that is part of the pattern match. Interesting. Let ampersand x equals ampersand 5 will make x equal to 5. So reference to x is a reference to 5. Yeah. Okay. I think that makes sense. That's cool. Thank you. And welcome. Nice to see you again. The trait append bar has only one function, which appends bar to any object. Implement this trait. Okay, so this declares the trait and says what things it does. So append bar takes self and returns a self, whatever type is implementing the trait. And we're going to implement append bar for string, which is supposed to append the string bar to the end of the string. And we see that here. We create a string s, which is foo. We append bar. We should get presumably foo bar. And if we look at the test, yeah, string from foo append bar gives us foo bar. String empty append bar gives us bar bar. Okay. So here we're going to have to have a function fn append bar self arrow self, you know, and we need, so self is going to be a string. Does it know that? If I say self here, so in fact, like, that'll compile but fail the test? Yes. So we're just getting empty string back. Well, we're getting our original string back. So in the test that passes in foo, we get foo back, and in the test that passes in the empty string, we get the empty string back. So we need to somehow append no, that didn't work. concatenate. I don't know how to append in strings. Rust, string, append. How do I concatenate strings? The internet will tell me things. Oh, go away. Oh, push stir. I knew that. Yeah, okay. So I can push stir, and that will push a string onto the end of another string. So self.push stir bar. Nope. Expected a struct. Oh, push stir probably doesn't return anything. So I have to return self. It has to be mutable. That would make sense. Hey, okay. So that all works. Yes, lots of methods in the standard library. And like, you know, it's one of these things, if you know a lot of programming, you figure there is a thing in there somewhere that does what you want, but you're not sure what it's called. And so the internet will save you. So, okay, so we needed it to be mutable because we're changing it with the push. And it's interesting that push doesn't, Rust push stir. I just feel like push stir. Yeah, so it doesn't return. Doesn't return anything. It takes a mutable self and a stir slice and tacks that stir slice onto the end, but doesn't return anything. Huh. Okay, well, that be that be. That's a little awkward that you end up having to return that like that, but eh. So there we go. I think we passed that, and that doesn't look too bad. Doodly doo, doodly doo. Go on to traits 2. Your task is to implement the trait append bar for a vector of strings. Consider for a moment what it means to append bar to a vector of strings. No boilerplate, you can do it. Let's look at what the tests think appending bar to a vector of strings means. So we create a vector with one string in it, foo, and we call append bar, and okay, now there will be 2 strings on the vector. The second, which will be the first to be popped, will be bar. So we'll put a new string bar at the end of the vector, leaving the rest of the vector alone. Okay, so we want to impl append bar. What's the syntax? For something. Okay, for vector string. And then we need a function, append bar. And actually, I assume if I don't have a function here, I'm going to get a compiler error that says, oh, vector not found in scope. Append bar, oh, it's because it's vec, not vector. Boom, boom, boom. Too many languages in my head. So yeah, missing append bar in implementation. So that's nice. So it tells us that we need to do the fn append bar self to self And so self in this instance is going to be a vex string, and we want to push self.push the string bar onto this, and they're using from, so we'll use the same syntax, string from bar, and then again we're going to have to return self. So we're going to push this new string on, we're going to return ourselves, and then fingers crossed that will be no, that didn't work. Hi, Luby Cat. Sorry that you have no sound. That's kind of a bummer. Sorry you have no sound. Okay, so this didn't quite work. Oh, it's got to be mute, right? Same as before. We're mutating the vector because we're pushing onto it, so it's got to be a mute. And now, hey, it does the right thing. So I'll be here until noon my time, which is just over an hour more. Nope. Sorry. Boop. Yeah, too bad about that. Sorry. Cool. Thanks for stopping by. Saturday. Same time. So, so I think we're done with this one. Yeah. I don't think there's anything very interesting happened here to talk about. So, boom, 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 boom. So we're on to tests, which are cool. I like tests. And actually I like at least I think I like the testing system in Rust. I mean, I haven't ever used it to write anything big. Oh, tests. Where? Oh, I opened the wrong test. I want this test. So I don't know how it scales, but I like it as an idea. I think it's kind of nifty. And I like being able to have them, in some cases, right there in the same file, but also have them in a separate file if you want to. I think that's kind of nifty. Okay. So tests are important to ensure that your code does what you think it should do. Tests can be run on this file with the following command, Rustlings run test1. This test has a problem with it. Make the test compile. Make the test pass. Make the test fail. So at the moment, things fail because we're asserting, but we're not asserting anything. In particular, we can assert that true is true, and that should pass. Yay! And we can assert more interesting things like 1 + 2 = 3, and that should pass. And we can make things fail by asserting false, and the test fails. We could assert, that 1 + 2 = 55, and that will fail also. Whoa! That's because I used a single equals instead of a double equals. And that failed. Good. So we can do all the things. So I'm just going to go back to true, and that will pass, and we can get rid of this. So that's pretty straightforward. So assert eq takes two things and checks that they're equal. It's interesting that you know, if assert eq had been a function instead of a macro, we would get arguably a more helpful error message that would say things like, this needs 2 arguments and you're not giving it any. Whereas here all we're getting is that there are missing tokens in macro arguments. And this is a general problem with debugging macros, is often they don't give you, the error messages aren't as helpful because you don't have the whole parser compiler to help out. So we can say those 2 things should be the same. Yay! And we can say those 2 things should be the same, and that will fail. And this gives us a more helpful error message. Before, when I had the double equals, we just had that the test failed. And here we get shown the left and the right, and we know we're in an assert eq, so we know that these 2 things should have been the same, and we get specifically what they were, which makes it easier to infer what might have gone wrong. So that's cool. And I assume that needs to be a macro to handle like really arbitrary types and things. I don't know. Yeah, I'm not sure. One could probably dig around in the implementation, but I have never done that. I've actually never really looked at any of the macro stuff in Rust. I know they exist. All the things with bangs are macros, but I've never really looked at how they're implemented. And I wonder if I'm going to want to, because there's a project I'm interested in working on where one of the concerns I have is how I'm going to handle like a really generic, like the implementation that we've been using is written in Clojure and relies pretty heavily on the lack of a strong type system in a lot of ways. And I think that when I get there, one of the things that I'm not sure how to deal with is there are going to be places where I'm used to being pretty loose about the types of things, and Rust is going to be all like, no, 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 you don't get to do that. And I'm not sure how to solve some of those problems and still keep it nice and general. Not for today, but it's a thing that I'm certainly thinking about. And maybe macros would be helpful there. Don't know. I have to think about that. Okay, so this test isn't testing our function. Make it do that in such a way that the test passes. Then write a second test that tests whether we get the result we expect when we call is even 5. Okay, so we have a function is even that does the right thing. It does mod 2 and returns whether that's 0. And right now we don't have any, we're not asserting anything meaningful. And so that's bad news. We need to assert that is even of 2, for example, is true. And then we got to fix this other one to say not is even 5. Is that the syntax? Yes, it is. Okay. Wasn't sure if bang was also used for negation. I think I've mostly seen it in the context of macros, so I was like, I'm not sure that's going to work, but it does. Okay, so we're just asserting that the function we call works, and I think the thing that is probably important to note is the use super : : star. Without that, we wouldn't have access to the is even function. Yeah. So this module is inside the module that is the whole file, but inner modules can't see outer modules by default. And so the inner module, we have to sort of say grab everything. So super is the outer module and star is everything. So it's like grab everything from the outer module and make it visible, which in this case gives us access to isEven, and we can actually use it in the test. And so you often see this kind of thing at the beginning of tests when they're in the same file. If they're in a separate file, you have to actually explicitly refer to the module by name. But in this case, since it's in the same file, we can just say super. Okie dokie. Questions, comments? Do 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 boom 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 bop bee. And what are we on to next? We're in a quiz. That's exciting. Haven't done a quiz in a while. Let me close the testing stuff. Quiz 3. Okay. So this quiz isn't testing our function. Make it do that in such a way that the test passes. Then write a second test that tests that we get the result we expect when we call ×2 with a negative number. No hints. You can do this. So ×2 takes a num, returns a num. No big deal. We use super again, so we have access to ×2. We have 2 tests. The first returns twice of positive numbers. So we call ×2 with 4, and we should get 8. And that should pass the first test. And it does. And then, there's this unimplemented. I'm not sure I knew that was here. No, I have seen that somewhere. I like that. In Java, I often will throw unsupported operation exceptions as sort of an equivalent of saying unimplemented, but unimplemented is nicer. I like that. So we want, as it says in the to-do, we want to replace this with an assert eq ×2 -4, and that should give us -8. Yay! So that was actually a remarkably easy quiz. It's a little surprising, maybe a bit of a bummer that that all they did here is a little bit of stuff with tests. I mean, because we've done options, for example. You could have included some option stuff here and maybe even some trait stuff, but not what they did. So, moving on. So we are gonna, where are we? We're in list, right? No, box. Standard library types box. Standard library types box 1. At compile time, Rust needs to know how much space a type takes up. This becomes a problem for recursive types where a value can have as a part of itself another value of the same type. So this would be things like trees and graphs would be obvious examples here. To get around this issue, we can use box, a smart pointer used to store data on the heap, which also allows us to wrap a recursive type. The recursive type we're implementing this exercise is the cons list. So if you're familiar with Lisp or any Lisp-like language, Scheme, Racket, Clojure, that crowd, all of those use cons lists. Each item is a I'm going to close that for a second. Oh, stop it. Each item in a cons list contains 2 elements, the value of the current item and the next item. The last item is a value called nil. Step 1, use a box in the enum definition to make the code compile. Step 2, create both empty and non-empty conlifts by replacing unimplemented. The test should not be changed. Okay, so we get a failure here because we have the enum list referring to the enum list, and that gives us an infinite recursion when the compiler is trying to compute the size of things. So the compiler has to know how big stuff is, because this is Rust, and the compiler really wants to know because it has to be able to do proper memory allocation and deallocation. And here, to try to compute the size of an enum, we'd have an I32 plus the size of a list. Well, the size of a list is an I32 plus the size of a list. Go, go, go. Yeah, you get the point. And so the idea is we wrap this in a box, and the box, yeah, so it's this, I think. Putting it in a box turns it into a pointer. So now this has a fixed size. It's an I32 plus the size of the pointer. And so the compiler can determine the size of a con cell and therefore determine the size of a list enum. And so it compiles, the tests fail because we've got some stuff that's unimplemented. In particular, create empty list isn't implemented and create non-empty list isn't implemented. So we're expecting create empty list to return a list nil. That seems easy. I can do that. List bang colon nil. Boom. So that should make that test pass. Yep. And then the other test, we are we're just checking that an empty list is different from a non-empty list. So that if we were to rather foolishly return nil here, the test would still fail, because we were expecting these to be different and they're the same. And so it's worth pointing out that there's an assert NE, which I'm not sure I knew was there. So that as well as assert equal, we can assert not equal. That's nice. So we need to have a list cons, and a cons is going to take two things. An I32, 0 is a good enough number. And then we might think that we would do this, but that's not going to compile because we haven't put that in a box. Yeah. So we expected a box but found a list. So we probably want to do a box new around that. Box new. Boom. Bop. Yeah. Cool. And we could also make something bigger if we wanted to. So we could, instead of having nil, we could have box new list cons 1 box nil. Another close parent at the end here, 2 actually. And so that would be a list whose first element is 0, whose second element is 1, and then is done. And obviously that notation will get very tedious after a while. If you're really going to do this, you'd start to create some helper functions to simplify this, clean this up, so it's not as nasty to look at. But it works, and that's cool. Okay. And by boxing this, this now ends up out on the heap. So we are sort of forcing things out to the heap here. So cool. Questions, comments? So then where are we next? We are at arc 1. So interesting that we go to arc. I would have thought we would have just done RC. Oh, but we're actually bringing threads in and stuff. Wow. Okay. So in this exercise, we have a vector of U32s called numbers with a bunch of numbers in it. We'd like to use a set of numbers with 8 different threads simultaneously. Each thread is going to get the sum of every 8th value with an offset. So we're summing them all up, but we're doing it in parallel and using different threads to add up different subsets of the array or the vector. So the first thread will do every 8th one starting at position 0. Second thread will do every 8th starting at position 1, so 1, 9, 17. Third thread will do every 8th starting at position 2, etc. Because we're using threads, our values need to be thread safe. Therefore, we're using arc. So arc stands for asynchronous reference count. And basically, if you have a pointer to some shared data that needs to be accessed by multiple threads, we use an arc, and the reference counting allows the system to know when it can free up the memory allocated for that thing. So if without something like that, if we passed some data to several threads, we wouldn't know when everybody was done using the data, and we wouldn't know when we could free it up. And in a garbage collected language like Java or Python or Ruby or Clojure, the garbage collector takes care of that, and we don't have to worry about it. But in Rust, we have to explicitly handle this kind of stuff because Rust is being very careful about the memories. So we're going to have to fill in a value for shared numbers where the first to-do comment is, and create an initial binding for child numbers where the second to-do comment is. Try not to create any copies of the numbers vector. So 4-bit unused imports. Interesting. And so we're going to use arc. We're going to use thread. So we create the vector. So this gives us the range 0 to 99 as U32s, and then collect pulls them into a vector. Shared numbers. So this, I think, is where we do the arc part, is my guess. So arc new numbers. So now shared numbers is, oh, I left a semicolon out. Wah, wah, wah. So shared numbers is an arc, so it is a shareable pointer to the numbers that will keep track of how many people have copies of that pointer. And when that drops to 0, then it will free the memory up, and it's thread safe, which is the A part. There's an RC that is not thread safe that you could use as well. So for each of the 8 offsets, now this is where we have to have the child numbers, and I think the thing to do here is cloning shared numbers dot clone. And if we clone the arc, we are only cloning the reference. We are not cloning the underlying vector. And so that's cool. It might seem like this is cloning like too much, but actually it just clones, as it says in the thing here, creates another pointer to the same allocation, increasing the reference count. So it doesn't copy the underlying data, it only makes a copy of the pointer. So this gives us a new copy of this pointer, which we can hand in here and give that to the threads. So it's weird that like they jumped us into this fairly complicated piece of thread code when we haven't actually done any threading. But so join handles is a vector, and we're going to push thread pointers onto it. And so we're going to spawn a new thread, one for each offset, and that thread is going to do whatever code is in this block. So it's going to take child numbers, which is the clone of the arc, and it's going to go through those. It's going to filter out only the ones that have the correct offset, and then it's going to sum them up. And then it'll print the sum of that subset at the end of that thread. And then if we join a thread handle, we wait for that thread to finish. So this loop basically says, let's go over all the threads for each thread, wait for it to finish, and then we'll be done. And when the threads have all finished, there shouldn't be any more pointers to our data, because shared numbers goes out of scope here, and all the child numbers go out of scope when the threads finish. Oh, and move here says any variables that the body references that are outside the body. In this case, child numbers is a reference to something declared outside the thread body. It gets moved into the thread, so the thread takes ownership. And that's why we have to keep cloning. So each thread will get its own owned reference to our vector that gets cloned and handed to it. So it gets its own pointer to the vector. So this all works. Yay, team. Why are we unhappy here? Oh, it just doesn't know how to, that's not a word that it knows. Now I think, for example, that we could drop shared numbers here and things will still work. No. Oh, I think does drop need a open? Is it a function? Yeah, okay. So we can at this point drop the reference to the this reference here, the first reference to our vector, because we don't need it anymore. And it will, at this point, it won't free up the vector until all the threads have done their thing. So we're still good on that. So nifty. Okay. I think that's all good. And I guess looking at the sums, we get different. Oh, and yeah, so it's worth noting that the threads finished in semi-random order because the threads finished in different orders. So the offset 0 thread finished first, but the offset 3 thread finished second. The offset 1 thread is down here. And in fact, each thread goes up by 13, I think. Yeah. So if we shift up by 1, at least for the early threads, everything goes up by 13. It might not be true at the end. Yeah, it isn't. We only go up by 12 in the end because I think we've walked off the end of the array here, because 100 is not a multiple of 8. So where we sort of fall off at the end is gonna vary from place to place. But coolio. I think that's good. I think we'll mark this as done. It is weird that there's all this thread stuff in that exercise. I think that's asking a lot, actually. but such is the way of the world. So here we're in library types iterators 1. No. Okay, so iterators let us iterate through collections, and they're very useful things. And I suspect there's 5 iterator exercises here. I suspect we'll use some and then reach a point where we're actually implementing our own iterators before the set of iterator stuff is done. I don't know. That seems plausible. So make me compile by filling the question marks. When performing operations on elements within a collection, iterate, yada, la, la. So, so we've got these fruits. And now we refer to my iterable fave fruits all the time down here. We call things like next on it. That means we need an iterator on that, which we can get by my fave fruits.iter. And I think that will make, yeah, at least that part compile. Now we got these question marks. So the first thing's going to be a banana, and then the third's an avocado, and the fourth is a raspberry. So we have to put in the custard apple and the peach. Some custard apple and some peach. And then when we call after raspberry, we've gone through everything, and ooh, got an ampersand there I don't need. Then that last thing's going to be a none. So this is how the iterator says we're done, is we return none in that instance. And so I think this will take care of that. Bum, bum, bum. Look at that. We are done. So that was pretty straightforward. So on an iterator, next gives us the next value in an option because the next value might not exist. There are also going to be a bunch of other things on iterators that let you skip over things and take the first 5 things. There's actually a bunch of stuff on iterators. I was looking at that yesterday or day before for other reasons, and it was like, whoa, there's a lot of stuff on iterator. Okay, iterators 2. In this exercise, you'll learn some of the unique advantages that iterators can offer. Follow the steps to complete the exercise. As always, there are hints if you execute Rustling. Yeah, okay. Complete the capitalized first function. So we're converting string slices to strings, capitalizing their first character. And we're calling input chars to get the characters. And C then is an iterator, which means C is not a great name. I mean, character iterator, I mean, something else would have been better than that. But, and then we're going to, C.next can either return something or not. And so we can get a sum variant or a none variant. If we have a none variant, we're going to just return an empty string. If we get a sum variant, we need to uppercase first and attach it to the rest. And so first dot to uppercase. Okay, that part was easy. Now what does to uppercase return there? It returns a to uppercase. Whatever the heck a to uppercase is. Now we can convert that to a string if we need to. So it's not a string. So I wonder if we can push. No. Is it push stir or stir push? It's push stir, right? Wah, wah, wah. Now I feel like I ought to be able to get everything else. So C is an iterator over characters, and if I convert it to a string, Rust convert iterator character to string. Okay, there we go. Collect. Oh no. Collect string. So I think that might do the thing. C dot collect. Does that work? Not happy. Oh, it's colon string. That syntax, I always get that wrong. This. Oh, push stir modifies in place. Yeah. Because we need the actual string here. Well, poop. That's annoying. I feel like there's a better way to do this. We'll get this to work and then we'll rummage around. So we would do that. Oh, but then we have to have a name for this. Let result be that result to that, and then result. No. Oh, no. Oh, I needed friends, and then I have to turn that into a string. Oh no, it is a string. And it actually wants a stir slice. So is collect too strong? Maybe collect is more than I wanted. Rust convert iterator character to stir. Join. Not obvious. I mean, join's a possibility, but that doesn't seem like the right answer. Yeah, I don't think join's the right thing to do. Well, we could borrow it. No, that does not, oh, because then it's, oh, result is going to have to be mutable. That definitely is true, because we're pushing onto it, so result's going to have to be mutable. Well, that didn't work. So we get our test. Oh, that's because, but actually I don't think, do any of the tests pass? Oh, 2 pass and 2 fail. So our tests that capitalize words pass and capitalizing the empty string pass, but these 2 don't. Okay, so we're headed in the right direction. But man, I don't know that I like that. That seems like a lot to me, and I bet there's a shorter way. In particular, this collect seems, but I need to say that it's going to be a string, and so I don't know. Well, I'm going to let it be. There's several other parts to this, so let's press on. If anybody's got any suggestions or thoughts, definitely feel free to share. Okay. So apply the capitalized first function to a slice of string slices. Return a vector of strings. So we have words, which is a slice of string slices. We're going to get back a vector of strings. We're currently returning just an empty vector. So we're presumably going to want to iterate over the words, return a vector of strings. Now I feel like this is a place where we ought to be able to do something like map. So words.map, no? Oh, I need iter. Dot map, no? Well, come on, iter maps, doesn't it? Oops, that wasn't what I wanted. Rust iter. So I want an iterator, and hello. There's iterator. Doodly doo. Okay. Yeah, there's all the stuff that iterators do, and that includes map. Okay, I don't know why it didn't autocomplete, but I ought to be able to map across that, because I want to do the same thing to every word in the slice. So I ought to be able to say map word, and I want to return capitalize first word, and that's going to return an iterator of strings, and so I think I collect that and I get a vector of strings, he says, hopefully. Hey, 3 tests pass, only 1 failed. So that's very pretty. This I still think is kind of ugly, but this is very pretty. I'm happy with that. So we're going to iterate over the words. For each word, we're going to use map. And I kind of suspect maybe map is not what they were thinking of here, because that's maybe a little advanced for where we are. But then there was that thread thing a second ago, so who knows? We're going to use map to capitalize each word. That's going to get it give us a new iterator back, and we have to collect those to get that to be a vec. If we don't have the collect, actually, no, I don't compile. Yeah, so we got a struct map actually out of this map, and so we have to turn that into a vector, and that's what the collect does for us. Put that back. Okay, step 3, apply the capitalized first function again to a slice of string slices, return a single string that we get by joining all that stuff up. Aha, now join would be useful. So we can in fact call capitalize words vector of words dot iter dot join, and let me look for join. Hij. Oh no, there isn't join. Rust join. Join in slice. So that takes a slice and a separator and gives us back the same kind of thing. Okay. So do we have to collect and then join? Oh, and I guess we have to have a separator, I suspect. Let's save. It'll shout at us. Method not found in iter, which means maybe we don't need to turn it into an iter. Maybe we can just join. And it's expecting one argument and it got 0. So if we put an empty string, hey, look at that. Okay, I was thinking that was going to be more complicated than that, but it is not. So, and I was also a little annoyed about having to call .iter here, because we had, you know, the last thing that happened up here is we called collect, which kind of undid the iter. Like we'd had an iter at this period point and we called collect to undo it. And I was like, oh, and then calling iter is the first thing here. That seems kind of, but it turns out join doesn't want an iter. It just wants a slice. So we can just call join directly on that. And that's very cool. Okay, that's pretty nifty. And I think there's nothing really interesting here. Yeah, I think we're good. So I still don't really like this part. I don't have any good answers as to what to do to make that better. It just feels that there's 3 lines in that sum clause. Seems annoying. But I don't have any thoughts. Nobody else seems to have any thoughts. I think we're gonna like call this thing done. Boom. And where are we going now? Iterators 3. Boom. This is a bigger exercise than most of the others. You can do it. Let's see, it's 11:38. So we'll see if we can maybe do this by 12, and then maybe that'll be the end of the day. My leg is definitely getting tired of sitting here. Here is your mission, should you choose to accept it. Complete the divide function to get the first 4 tests to pass. Get the remaining tests to pass by completing the result with list and list of functions, a list of results functions. Okay, so we have an enum division error that returns not divisible with a not divisible error, or a divide by 0. And I presume divide by 0 is something built in. And a not divisible error has a dividend and a divisor. Calculate a divided by b if a is evenly divisible by b. Otherwise, return a suitable error. So if b is 0, we presumably want to return a divide by 0. If a mod b is not 0, we want to return a not divisible with the two pieces. Otherwise, we return the result of doing the division, and this is all in a result thing because we need to be able to either have a result or have an error. Okay, that I can do. So we could use an if, or we could use a match. I think I'm just going to use an if. I don't know if that may not be the rusty way to do it. Maybe a match is more what we would expect. I don't know. Kind of feel like a match is more what Rust people would do. Not sure. So if that's equal to 0, then we'll return a divided by b. Else we'll return, actually maybe we'll make this put the two error cases first. Division error, not divisible error, dividend gets A and divisor gets B. So that should make oh right, expected result found I32. So yeah, right. So if there's we can either return a division error. Oh, actually, we need yeah, we need well, let's we know we need result is either going to be okay or error. So this will be okay. And I think we need ers in front of all these guys. To signal that this is going to be an error. So that will help some. Try to construct one of the enums variants. Division error. Oh, colon, duh. Syntax. Learning syntax. Okay, we're heading in the right direction. And I've got braces wrong somewhere? What? Did I miss? Yeah, I've got too many close parens there. Okay, that was the problem. Variant, not divisible, error not found here. Oh, it's not divisible, not divisible error. Good grief. We'll get there. I misspelled something? Okay. What have I done now? It doesn't like the fields. Division error not divisible is a tuple variant. Use the appropriate syntax. Division error, : not divisible. Oh. It says it wants these in round braces. Why? Okay, well, we could do that. And then I think I don't have to repeat the names. No! Ah! Mark! I'm going to go back here. I do not understand the error that it is giving me. Oh. That's because I'm missing a open curly here. So that takes care of that. Oh, I probably don't want. What? Oh, yeah. And now, I don't think I want parens. Yeah, I don't want parens here. Boo, doo, doo. Oh, come on. Put a space there. Da, 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 da. Okay. Now save. Now we should be back, I think, to where I was a little while ago. Okay. Division error, : not divisible defined here. Okay. Not divisible. Field does not exist. Oh. This is not divisible error. So I've got more nesting. Okay, so we have division error, not divisible. Not divisible takes as an argument a not divisible error. So that needs to be open paren, not divisible error. And it will take the curly brace bit. That closes that, and that closes that. Oh. Is that right? Yes. Okay. So, yeah, I'm clearly, in some sense, all of this was obvious, but yet I obviously didn't know what I was doing. And flailed a fair bit there. But it's all like written right here, right? It's I want a not divisible error, okay? And a not divisible error takes a dividend and a divisor. And a not divisible error sits inside of not divisible. So it is because of the round braces here, we need round braces. It is an argument to this. And this is a variant inside that. So we need division error, : not divisible, open paren, not divisible error, arguments. Dun, 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 dun. Okay. So that passes the first 4 tests. So we complete the divide function. We got our first 4 tests to pass. Now we get the remaining tests to pass by completing the result with list and list of results function. Whew. Complete the function to return a value of the correct type so the test passes. The desired output is OK and a collection of numbers. So, and if we look at, let's see what failure, test result with list. Yeah, so we're expecting OK and a collection. So we need to return a result type. And it's going to be a vector of numbers. I32 to pick a value. Is there anything down here that would tell us? No. Oh, yeah, and we have to have an error type. What can go wrong here? Well, I guess we want a division error. I guess? I mean, it's not obvious what so all of those numbers, 27, 297, 38, 502, so check that, 38, 502 divided by 27, yeah. So all of those numbers evenly divide 27. So we're going to assume here in some way that everything works. And there isn't a test that checks that everything doesn't work. So they don't give us a guideline as to what to do if this fails. So, I don't know, we could just return any kind of error. It doesn't really matter a lot, but probably makes the most sense to return a division error that maybe is the first error that we run across. Seems like a thing. So now that compiles. And now we have to actually like return something because we're not returning anything yet. So numbers into iter. We map divide n by 27. That's going to give us a whole bunch of result types. And well, I'm glad you think so. We'll be here only for another 10 or 15 minutes. I'm going to try to finish this exercise, but I'm here every Tuesday and Saturday from 10 to noon, my time, which is Central Daylight Time in the United States. We'd love to have your company. So if we just said collect here, that is not going to do a good thing because we're going to, because I got a semicolon, we got unit type, still have unit type? Blah, blah, blah. Well, here's just a division results. What if we return that? Oh, 5 of our tests pass. Really? So that worked? So map over result. Oh, I guess just that, well, no, but why? these are all going to be sums, or OKs, sorry. So these will all be OKs. And if we collect, what magic causes the OK? Whoa, oh, collect. Oh, so if you have an iterator of results, collect can give you a result of the iterator, the collection that we get by bringing the things in. Oh, I didn't realize it would do that. That's actually kind of nifty. Is there an example down here? If you have a list of result, you can use collect to see if any of them failed. So if you OK, error, OK, bad, we collect, and that gives us the first failure. And if they're all good, we get the values. I'll be darned. That's kind of nifty. Okay, so this collect, because everybody divides, in this case, evenly, we get nothing but OKs, and the collect basically strips out the OKs and gives us a result type back. So division results is a result type, and that's what we're supposed to return here, and life is good. So that passes. I'll be darned. That is nifty. I didn't know that would even work. Cool. So then the last test to fail on this is here we're expecting a vector of results instead of a result of vectors. So we want, this is going to be a vec of result of I32 and presumably a division error. Oops, division error. And again, all these divide evenly, so we won't get any errors. And so we would take the numbers, turn it into an iterator, map across, and now we will get the vector of result types that we were looking for. I got my angle brackets wrong there. Boom. Because it's the result that takes the two types, and vec takes a single type, which will be the result type. So fingers crossed that'll work. No. Oh, that's because I didn't return division results. I'm not sure that the name division results is super helpful. Oh, I've got to collect. Yay! Oh, hang on. Oh, this is super weird. Okay. So this line and these two lines are identical. And yet they return different things. And it seems like they should have been different, but the reason it works is that collect can, as it were, look at what type is expected and collect accordingly. And so here collect says, what do I need? I need a result of vec. And so it uses that trick that if it's got a vector of results, it will collect them into a single result of a vector if that's what we want. And so it uses that magic here. Here it says, what do we want? We want a vector of results. We already have. Well, we have an iterator of results, so we will collect them into a vector and we're done. and we won't do the sort of further collapsing into a single result object. So the fact that these lines are the same but return different things is because Rust is looking at the return types here and making a decision about what version of collect to use to generate the desired type, which is kind of weird, kind of cool, kind of weird. So yeah, that's interesting. Okay, well, and that works, and it's 11:59. I'm going to call that a thing because I think that's, yeah, okay. So we still got so this will take us to iterator 4. Yeah, so we still have 2 more iterator exercises, and I need to bug because we got some other things coming up this afternoon. So I think we'll quit there. We made a lot of progress, got through a lot of pieces, so pretty happy. Thanks for all the suggestions and the help. I appreciate it, and for joining me today. We'll be back. I'll be back Saturday, 10 to noon, so same time as today, Central Time, and we'll keep working through these. And hopefully we'll finish these rustling exercises in maybe 2 more sessions, depending on how complicated some of these other exercises are, and then start working on an actual project that I want to actually make some progress on. So yeah, that'll be a thing. So thanks for joining me. And here I'll remind everybody of the handles everywhere, and I will see everybody later. Thanks a lot.